This instructional video will show how to use the method of initial rates to determine the rate law for a reaction when you're given experimental data that shows the concentrations of the components of the reaction at the beginning and the rate of reaction at the beginning. Now in this example, units are also suppressed just for speed and clarity of writing the mechanics. Now, the generic form of any reaction rate law requires that the rate be equal to a rate constant times the concentration of the components, where the individual components have an exponent that is equal to the order in that component. So we'll use a red M on the oxygen and a blue P on the hydrogen. These are determined from the data in this method by comparing trials. So I'm going to compare trial number 1 versus trial number 2, and I will also compare trial number 1 versus trial number 3. And these will both give me some information. Comparing trial 1 versus trial 2 shows that the rate does change, oxygen does not, but the hydrogen concentration does change. Because that rate change is due only to the hydrogen, that will give me P. Now, the second comparison I'm going to make is 1 versus 3. Again, we see that the rate changes. However, this time, the hydrogen concentration does not change. And so all of the change in the rate has to be a result of the change in oxygen concentration. And because of that, that comparison will give us a value for M. Now, in order to do this, we want to be able to compare the values of the initial rates for the two things under comparison. So, looking at rate 1 versus rate 2, what we observe is that 0.45 is 1/2 of 0.9. So, rate 1 is 1/2 of rate 2. I multiply that by 2 and I'll have an equality. The reason that's important is that I know that rate 2 is going to be equal to something I can simply write out. We have our rate constant, we have our oxygen concentration, 0.15 raised to the M. Our hydrogen is 0.2 raised to the P. And now I can erase here, remembering that I'm doing 2 times whatever I would write out for rate 1. And so that's the rate constant. Our oxygen concentration in trial number 1, 0.15 to the M. Hydrogen concentration, 0.10 raised to the P. So now, by way of comparison, I can find things to cancel out. This quantity and this quantity will both cancel. Because I want to solve for P, I'm going to isolate that variable. I'll divide both sides by 0.10 raised to the P. And so we get cancellation here, leaving with 2 equals 0.2 over 0.1, all raised to the P. Well, 0.2 divided by 0.1 is just 2. So that means that 2 equals 2 raised to some power. So that power P is equal to 1. And so now I know that this is first order in hydrogen. I'll do the same thing by starting off comparing rate 1 and rate 3. Now, 0.45 versus 3.6. I could substitute in the values and do all of the math and figure out the difference between these two quantities. Or I can recognize that we have a factor of 8. I did the math in advance. It's the only reason why I did. And so now because we have this equality, I can write out everything for rate 3. We have the rate constant, and we're going to have 0.30 for the oxygen concentration raised to the m, 0.10 raised to the 1, because we now know that. And I know that I have 8 times rate constant, 0.15 raised to the m, 0.10 raised to the first. And so here we're doing the same thing with our cancellations. I have the rate constant on both sides, which will cancel. I have 0.10 on both sides, so these will cancel. And now I just have to divide through by 0.15 to the m on both sides. And so this cancels out, leaving me with 8 equals 0.3 over 0.15, all raised to the m. Well, 0.3 divided by 0.15 is going to give me 2. So 8 equals 2 raised to something. This means that for m, I get a value of 3. And the reaction is said to be third order in oxygen. Now that I have all of this information solved out, I can write out the complete form of our rate law. And so the rate of reaction is equal to our rate constant times oxygen concentration to the third power, hydrogen concentration. So it is third order in oxygen, first order for hydrogen, and fourth order overall. That is finding the rate law using the method of initial rates.